Alright, so now let us look at a problem how to calculate the reliability index beta for a given beam. Okay, so this problem that I am going to discuss is the example 8.1 of Ranganathan textbook. So let's see what the problem says. Calculate the reliability index beta. Beta is the reliability index of the beam against limit state of collapse subjected to self weight Q1 and live load Q2. The flexural resisting moment capacity of the beam is R, the resistance is R, and what are the other data given? Mean value of Q1 is 400 newtons. Now you have to be very careful with the units here. I'll let you know why. Mean value of Q1 equals to 400 newtons, sigma of Q1 equals to 10 newtons, mean value of Q2 equals 5000 newtons, sigma value of Q2, which is if you see the picture here, the diagram here, Q1 is my self weight of the beam and Q2 is the point load that is being applied on the beam. Okay, so mean value of Q1 is 400 newtons, sigma, the standard deviation of Q1 is 10 newtons, mean value of Q2 is 5000 newtons, sigma, the standard deviation is 2000 newtons, mean value of R is the resistance of the beam. The mean value of the R is 10,000 Newton meters because it's a moment, and the mean value of the standard deviation of R is 1000 Newton meters. Okay, so this is the problem that we have here. Q1 the self weight I have already mentioned, and Q2 is the point load. Okay, now how to move about this? Okay, so first I have to find out S. S is my action, right? Now this action is due to the combination of Q1 and Q2. Okay, action is due to the combination of Q1 and Q2. Just don't add them up. It's a combination of some combination of Q1 and Q2. And here the R that I have is R is the resistance, the moment resistance of the beam, which means I have to find out the action S as a moment that is being developed due to Q1 and Q2. So Q1 is my self weight. Okay, so now we have to be careful regarding, suppose we have self weight. Self weight is usually a UDL, right? We know that the self weight is usually a UDL. Self weight is usually UDL. If it is W, then the moment due to self weight that I am going to get, the moment due to self weight I'm going to get, and since this beam is simply supported, is going to be WL square by 8, right? I already know this. It's going to be WL square by 8 if W is per meters, is the UDL, as a UDL. And if it is not as a UDL, if it's combined, if it's given as a combined load, which means W into L is your combined load into L by 8. Right? W into L is the combined load. UDL times the length is the combined load into L by 8. Now if we go back here, Q1 is supposed to be the self weight, right? And here the unit is given in 400 newtons. It's not Newton per meters. Okay, even sigma R is given in newtons. It's not Newton per meters, which means Q1 here is the combined self weight, not the UDL. Not in the UDL form, although the self weight is acting in a UDL form. Here we will have a combined load here. Okay, which means I'll have let me write here. Okay, the moment due to self weight shall be so W into L now here is Q1 for me, Q1 into L by 8. Okay, and the next one is moment due to the point load. Point load is Q2, and I know L by 4, PL by 4. The point load is P. If the point load is P, then I'll have PL by 4 as my moment, the maximum bending moment. Okay, so finally what I can say is S equals Q into L by 8 plus, Q1 into L by 8 plus Q2 into L by 4. And L given here is 4 meters. Okay, so this one equals Q into 4 by 8 plus, again I'm making the mistake, Q2 into 4 by 8. Okay, oh sorry 4 by 4. Okay, so 4 by 8 is 1/2, so Q1 by 2 plus So this is S. M, which is going to be the margin of safety or the failure function, equals to R minus S. So equals R minus Q1 by 2 minus Q2. So this is my failure function equation. Now what will I get? I need to find out mu R, because here the question is determine where is it? Yeah, calculate beta, which means the reliability index of the beam. So the reliability index, in order to find out the beta should be mu m by sigma m. So I need to find out mu m and sigma m, given m is this. So let me just change the page. Oh, alright. Yeah. So let me rewrite the m equation. M, the margin of safety, equals R minus Q1 by 2 minus Q2. Okay, so from this, mu m equals mu R minus half times mu Q1 minus 1 times mu Q2. Now you see one thing, this half is when I'm taking the derivative of m. How do I get half? This half value, if I take the derivative of m with respect to q1, okay, then I'll get minus half. And if I take the derivative of m with respect to q2, I'll get minus 1. Okay, so this is where actually I use a Taylor series expansion in order to find out. You don't need to see how it comes. I'm just informing you that the first order Taylor series expansion, this helps me give the derivative of m with respect to q1 minus half, and of m with respect to q2 equals to minus 1. So which means I've already found that mu m equals mu r minus half times mu q1 minus mu q2. Okay, and what about sigma m then? Sigma m would be, or sigma m squared, let me be very specific, is going to be what? It's going to be what was sigma r? 1000, is it? Okay, fine. Okay, so this one is going to be del m by del q1. Del m by del. I don't have anything here. Okay, del m by del r. If I do del m by del r square times sigma r square plus del m by del q1 square into sigma q1 square plus del m by del q2 square into sigma q2 square. Okay, so this is what usually the equation is supposed to look like. So if I'm going to simplify del m by del r, if I see here in this equation, if I go to the top, del m by del r if I do is 1, del m by del q1 I have already found out, del m by del q2 was also found out. So del m by I'll write here that del m by del r equals 1. Okay, because you can see here, if I take a derivative of m with respect to r, I'll get here 1. Okay, so therefore okay, I'm in the screen view. Sigma m square equals 1. This is 1, so this is sigma r square plus del m by del q1. Del m by del q1 equals minus half. Minus half square is half squared. Okay, sigma q1 squared plus that one is minus 1. Del m by del q2 is minus 1. So this is minus 1 squared into sigma squared. So this is sigma q2 squared. Okay, now we have all the values here. We have mu r given, mu q1 given, mu q2 given in the problem. Okay, I have sigma r given in the problem, sigma q1 given, sigma q2 given. So you can just pause the video, substitute the values, and then we'll find out the values of mu m and sigma m. So I already have the values because I'm just seeing it from the book. I'm not even calculating it myself. So mu m I am getting, if I put it in that equation, I'll get is 4.8 kilonewtons. Okay, and sigma m, when I put in that equation, I'll get 2.236 kilonewtons. Kilonewtons. So reliability index beta, final thing, is equal to mu m by sigma n. So equals 4.8 divided by 2.236. So this one is 2.147. Now suppose it was asked to find out the probability of failure even. So what would you do? It's not given in the problem, but suppose it's asked to find out the probability of failure. I'll just do shy of 2.147. So whatever value I'll get, this is going to be the probability of failure. Now you can go through the other problems and see that how other terms, in the other terms, how can I find out the various values. But one thing I would like to say here is there are various ways in which R and S can be distributed, right? So both R and S can be log normal, both R and S can be normal distributions. So in that case, how this beta value we can find out is, suppose if if both R and S are normal distributions, both R and S are normal distributions, in that case mu m equals mu R minus mu S. Okay, because my failure function is m equals to R minus S. Okay, therefore mu m equals to mu R minus mu S, and sigma m equals sigma m square, to be very specific, sigma R square plus sigma S square, right? Because if I take a derivative of m with respect to R, it is 1, and with respect to S is minus 1. So squared hit here, you will get 1 squared and minus 1 squared. So this is when you have a normal distribution. In that case, beta equals beta equals mu R minus mu S divided by sigma R square sigma S square whole to the power half, which means root under of this one. Okay, so this is beta, and the probability of failure probability of failure would be shy of mu S minus mu R, because I have a minus here. Remember that it's minus beta, right? If you go to the back to the equation, and this phi of minus beta, so phi of minus of mu R minus mu S is mu S minus mu R, sigma R square plus sigma S square whole to the power half. So this is how you find out the reliability index when both R and S are normal distributions. If both R and S are log normal, in that case what happens, if both R and S are log normal, then my failure function m or the margin of safety function is R by S. Okay, is R by S. So in that case I will directly write down beta equals natural logarithm of mu R by mu S divided by delta R square plus delta S square whole to the power half. What is delta R? Delta R is standard deviation of R divided by mean of R, and delta S is standard deviation of S divided by mean of S. What is it called? Coefficient of variation. Coefficient of variation, if you remember, is standard deviation divided by mean. So in case of if both are log normal, you will simply find out beta by ln mu R by mu S divided by the coefficient of variation of r squared plus coefficient of variation of s whole squared. Okay, and suppose if you have to just see a graphical way in which I can find out from the distribution function itself. So if this is a normal distribution, okay, and so this is my mu m, which is my mean, okay, and here is the point 0. So anything beyond this is failure. So this is m less than 0, and here is m greater than 0, okay, and this is m, which is r minus s, okay. So this and this distance is beta times sigma m. Okay, how did I get this? Because beta equals mu m by sigma m, which means mu m equals beta times mu m equals beta times sigma m. So beta times sigma m, this is mu m, the mu m value, which is beta times sigma m. Okay, and if m is a log normal function, which means both r and s are log normal, in that situation what happens is you have a graph like this. So this is your log normal function, something looks like this, okay, and this is mu m, same, okay. Here too you have 0, so this is m less than 0, all are failure, m greater than 0, all are safe, and m equals ln r by s, log normal ln r by s, okay, and same, this distance is beta times sigma m, okay. So I request you to go through the other problems also, the subsequent problems, and come with me with whatever doubts you are facing in those problems in order to calculate the reliability index beta. Anything else, then I'll just upload a video and discuss with you in the next class.